Okay, I'm just going to say hi as well so you can see who I am. My name's Adrian Jackson. I'm teaching this course today. As I say, my colleague Ellen is around to help with issues and questions as well. I'm not going to leave a video on all the time because I find it distracting, let alone yourselves. So I will switch it off in a minute, but it's always nice to say hi for people to be able to see who's teaching them. As I said, possibly whilst I was on mute, apologies. If you have any questions about the material or about the course in general, about ARCHER2 in general, or any issues as we go in, please do feel free to ask questions as we go along in any way that suits you. I should have also shared up front. Hopefully you all know this, but let me just switch what I'm sharing and share a different screen. The material that we're all teaching today is all online at the ARCHER2 website. So this is the course page. Hopefully you've all seen this because you've signed up for the course and you've hopefully found that through the ARCHER2 website. So we have this ARCHER2 today's ARCHER2 for Data Scientists course here. This is the timetable we're going to loosely follow. But more importantly, the course material is all here on GitHub. So the lectures that we're going to go through today are all here. You can take those and have a look at them. And the exercise material we're going to use is here as well. And so those are important resources for what we're doing today. There is also a course chat where you can put questions and comments in as well. So keep an eye on that as we're going through. So you have a plethora of different ways to ask questions if you want to. Right, let me just get back to the lecture and we shall get going. So like all our ARCHER2 courses, you're free to reuse the material. The lectures and the practical material is shared under Creative Commons license. As long as you attribute us, that's fine. Okay, so we're just going to start off with a little introduction to what ARCHER2 is. At points throughout this training, I'll call it ARCHER by accident. Apologies. ARCHER was the previous incarnation of this computer. ARCHER2 is its replacement, but my brain hasn't quite caught up with that. So quite often I just call it ARCHER. If I call it ARCHER, I do just mean ARCHER2. So ARCHER2 is a large-scale computer provided by the UK research councils, or at least EPSRC with a little involvement for some others, which provides computational resources for academics to do simulation and data analysis and these kind of things. It's something that we run for the research councils at EPCC, although the hardware and the actual system itself comes from HPE Cray. But one of the things that the research councils do is fund other things around and about the service to help people use the system, one of which is the training we're on today. So we have this funding to provide training to help people use the system and to exploit it efficiently. Again, hopefully you know this because you're here. This is what ARCHER2 actually looks like. It's a big set of computer racks all connected together with a nice pretty picture on the front. If you open it up, then you can see all the cooling and the cabling and things like that going on in there. But that's what ARCHER2 looks like. It doesn't actually sit where we work in the EPCC in Edinburgh. It actually sits, we have a machine room, a facility which sits outside Edinburgh called the ACF, and that's where it lives. Not that you care about that. And alongside ARCHER2, we have the website, which has quite a lot of documentation. So a lot of the things that we're going to be talking about today, you can find more detail about on the ARCHER2 documentation. Plus, as I say, we have a range of training courses and past training course material there, which can be useful if you want to look in more detail at some other things like parallel programming or some particular applications. As I said, my name's Adrian Jackson. I'm a senior research fellow at EPCC, but I do quite a lot of teaching on our master's course, PhD students, and things like this ARCHER2 program. In my day job, I am mainly looking at research into high performance computing and helping other people use high performance computing. So the teaching fits quite nicely in there. ARCHER2 has a help desk, so if after this course you're still using your guest accounts, and we'll come into what those are, but into your course accounts, should I say, and you have any problems, feel free to get in touch with me through this email address here. But more widely, we have what we call a service desk now, which I still call a help desk, where queries can be sent on ARCHER2. You know, I'm having problems accessing the system. Can you help me install this software? I'm not getting good performance. These kind of things. There's a service desk which deals with all those kind of things. And that easiest way to access that is through an email address, support@archer2.ac.uk. And in that spirit, we are also looking for feedback on the training we give. So there'll be a questionnaire or feedback form for you to fill out at the end of this course. It's not very onerous, but it is useful for us in evaluating, you know, what are we teaching well, what we're teaching badly, what are we missing out on, and those kind of things. So if you can fill that out at some point after the course is finished, that would be very useful for me. Okay, so to provide you access to ARCHER2 to allow you to try out some of the things we're talking about today, you get given, and hopefully you're all aware of this, but if you're not, now's a good time to sort this out. You're given accounts on the system for the duration of the course and for up to a month after the course finishes. So what we do is we set up a project for this course on ARCHER2, and inside that project you each get an account with a certain amount of budget, and that lets us run the exercises for today's course, but it also lets you use it afterwards to try out things on the system as well. So as it says here, these accounts will be provided for up to a month after the course finishes. 2 weeks after that month period is finished, once the account stops working, the accounts will be properly closed down and then deleted. So what that means is if you want to keep any material that you've developed today or in the next month, by the time we come to closing your accounts, you should copy it off the system so you don't lose that elsewhere. But you'll be reminded about that before it happens. And it's actually a lot better than it used to be. When we were doing this on the Archer service, we used to just give you guest accounts for the duration of the course, and you had to copy things off directly at the end of the course, and that was it. Now you get, you know, up this month period after the course finishes, plus a little bit of grace beyond that to get any files if you suddenly decide you need some data or files off the system. All our ARCHER2 training courses follow a code of conduct, which you can find on the web page. Basically, it just means we expect people to behave sensibly and nicely to each other and the trainers as we're attending the course and giving the course, and that applies to me as well. If you have any problems regarding conduct on the course, then there's on the website where this code of conduct page is, there's a incident reporting form you can use there. And then finally, I say finally because I've probably got, yeah, so finally, ARCHER2, as well as providing training courses to help people use the system, there is also a sort of funding program associated with ARCHER2. This is called the ECSC Program. And the ECSC program lets you bid for money or people's time to help improve codes for use on ARCHER2. So you effectively put in a small funding proposal where you can ask for up to 12 months of effort for either hiring somebody locally or for somebody like me at EPCC to work on a code, either porting it to ARCHER2 to make sure it can use the system or optimizing it in some way so that it can efficiently use the ARCHER2 system. There's much more detail on the web page, but it's quite a nice little funding scheme, which is lighter weight than like a full-scale UKRI grant proposal, and generally easier to get. So the success rate is about 50%, I think, for the ECSC proposals. And it lets you fund things which are quite hard to fund, usually through general research funding, through UKRI research funding, so namely development of program and optimization of programs. So it's worth being aware of. The web page has more details, and if you have any questions about that, do let me know, or get in touch, and I can forward you on to the right people. Okay, so what is ARCHER2? ARCHER2, as I said, is a big HP Cray system. It's about 6,000 servers put together, what we call nodes. Each one of those nodes has 128 cores inside it. So that means there's about 750,000 cores in the system in total, so it's quite a big compute resource. Actually, each node is made up of two 64-core processors, so it's a dual socket system. And like all big parallel computers, it's accessed via batch system. The batch system we use is Slurm on ARCHER2. So the batch system is the way you interact with the compute nodes. It's the way you can submit work, submit jobs, and they're run for you. And it also has a slightly more complicated file system setup than a lot of computers you may be used to. So we actually have two main file systems, home and work. And so here it's sort of home. When you get an account created on the system, you get given an account directory both on the home file system and the work file system. And so in this example, if your project code is TA062, this would be /home/TA062/TA062, and then the username you've chosen. But you also get given a directory on work. This is important because the work file system is the only one you can see from the compute nodes. So all jobs that run on the compute nodes need to have their data and programs on the work file system. And that means we need to make sure that we put things there that we're going to run on the compute nodes. When you first log in, you're always on the home file system. This is the one that's backed up and is a place that keeps off important programs and things like that. But as I say, it's not accessible from the work file system and the compute nodes. So what we say is actually generally just go straight onto your work directory and do everything in there, and then you won't run into any problems where you submit a job and it fails because actually the compute node can't see the data you need or the applications you need. Again, this sounds complicated. It's not really once you get used to it. It's just we have multiple file systems for different things. Make sure you're using the right one if you want to run computational jobs on the system. Okay, this is the timetable we're going to loosely follow today. We'll try and stick to the breaks and the lunch times effectively. But what you can see is that we're going to cover a range of different material here. So ARCHER2 for data scientists, it could, teaching a system for data scientists could cover very large amounts of material. There's lots of different things that could be here. We could look at how you become a data scientist or what you mainly do as data scientists. The approach we've chosen for this course is really to say, actually, let's assume that you know what you're doing in data science and you know the tasks you want to do and you're already familiar with doing data science work. How would you do those commonly on a system like ARCHER2? So what we're trying to teach you is what ARCHER2 is suitable for, how you can run your particular workflows on ARCHER2, so how you can run your software, get your data on, get your data off, how you can install new software as is required on ARCHER2, and then using the hardware as efficiently as possible. So you can get jobs up and running, but are you running them in the correct way? So we're not looking to try and teach you how to do data science yourself, and we're not focusing on one particular data science tool like pandas and say, you know, this is all you can do about pandas. If you're interested in any of those topics, we do have other courses you can have a look at. There's a data carpentry course we run where we introduce basic data science tools and basic data science approaches, and some of that material is on the ARCHER2 website. You can go and have a look at it. We teach other courses which teach you the basics of of data science, or the basics of Python. For instance, we also run a scientific Python course, but that's not what we're going to focus on today. We're going to talk about the ARCHER2 hardware. We're going to look at containers because this is an important method for running your software on the system if it's hard to install or complicated to install. And then we're going to look at two of the commonly used sort of tools for data science, Python and R, and how we can use those on ARCHER2 and how we can use those to get efficient or parallel usage of resources on a system like ARCHER2. So that's what we're going to go through. That probably means that we won't cover everything that's useful for you. It probably means that some of the bits may not be of use to you. If primarily you're an R programmer, then the Python stuff might not be as interesting for you. If you're a Python programmer, the R stuff might not be as interesting for you. Apologies for that. But what we're trying to do is give you sort of a broad set of understanding on what's on the system, how to use the system, and how to use it efficiently for things that data scientists commonly do. Ultimately, hopefully the course is useful for you, but also hopefully it's enjoyable, or at least not too boring. But the best way for you to get good use out of the course is for it to be interactive. So if you have any questions as we're going along, or for things that don't make sense, or if we're not quite covering the bits of Python or R that you'll be using and that raises questions, do just let me know, and we can discuss those kind of things. Okay, is there any questions before we go on to the first lecture? Because that wasn't actually the first lecture, that was just the intro. The first lecture, what we'll do is actually talk about ARCHER2 itself. Whilst I get that up, you still can ask questions. And just share the screen again. Okay. Right, so we've had a look a little bit at what ARCHER2 is, but we'll go into it in a bit more detail here to try and give you enough of a background information so you can make choices about where to run, well, whether ARCHER2 is suitable for what you want to do, and then if it is, where to run specific things and what things need to be taken into account when looking at optimization or looking at making things run efficiently. So as we've said already, ARCHER2 is nearly 6,000 compute nodes, and it has these file systems, but of course there's more to it than that. Particularly one of the things that differentiates a high performance computer from other kinds of computers is the fact that it has a high performance network connecting together all those individual nodes, all those individual servers. So here we're using the HPE Cray Slingshot network. That's also the thing which connects the compute nodes to the file systems to give it high performance and high bandwidth, low latency access to data, which of course is likely to be important for data science work. To facilitate users getting access to the system, we have login nodes. So you never yourself, let me get a pointer up. You never yourself go directly onto these compute nodes here. These are what's controlled through the batch system. What happens is when you log onto the system, you log into these login nodes here. We have 4 of them, but that doesn't really matter to you. You just get assigned a login node when you go in. There are actually also two what we call data analytics nodes. They're called data analytics nodes, but not really designed for large-scale data analytics. What they are is nodes to run jobs on, which would be a waste to run on a compute node, but they still take a long time, so you don't want them running on the login nodes. I should back up slightly. When we give out compute nodes through the batch system, when you submit a job to the batch system, the minimum unit we give out is a single compute node. So that's 128 cores. So that's sort of what we call the minimum chargeable unit. If you ask for something, you'll get at minimum 128 cores. This is done on purpose because if multiple people are using the same nodes, you can get interactions between different programs causing performance problems for people. So we minimize that by saying, well, at the minimum, you get a single node to yourself and no one else is using that node, and then you can have more nodes if you want. But of course, if you want to just do something like run a single program to zip up some files or unzip some files or download some files from a repository somewhere, or you want to compile something in which it takes a long time and a lot of resources, it's a waste of resources to ask for a whole compute node with 128 cores and only use one of those cores to do your job. So that's what these data analytics or nodes are sort of designed for, things like single process jobs, copying data to systems, copying data from other systems to ARCHER2, downloading data sets, doing some small amount of data processing there. But we won't generally be using those today. They're just a useful resource to know about. As I've already said, there's these two file systems, the home file system and the work file system. You may ask, why do we have two separate file systems like this? Well, basically, it's because we want some place on the system where data can be backed up. So if users make a mistake, it's retrievable. But that kind of file system generally is quite slow for large-scale data work, large-scale I/O, input-output work. And so we have a separate file system, which is the work file system, which is designed to be fast for jobs to read and write data from, but it's not backed up. So the data could be lost on there, but it enables that fast access to and from the data from applications. To make sure that jobs don't damage their performance by going out to this slow home file system when they're running by accident, we don't make that available from the compute nodes. So that home file system you can't see from the compute nodes. You can see it from the login nodes and the data analytic nodes, but you can't see it from the compute nodes. From the work file system, you can see from everywhere. So you can copy data from the home file system to a work file system from the login nodes or the data analytic nodes. And then, of course, you can use it from the compute nodes. There are actually more file systems available. At some point, we're going to have this solid state storage file system up and running, which is a high performance, even higher performance file system than work, but much smaller. Actually, it's not in production yet, so it's not being used actively by users yet. But if you're into data analytics workloads, if that's what you're going to be doing and you're processing large numbers of files or you're producing large numbers of files, in the future, this is likely to be something that you want to exploit because it lets you have higher reading and writing performance from files than the parallel work file system. So that may be of benefit you in the future. Now, again, this is a lot of detail here. I don't expect you to remember it all or necessarily for all of it to make too much sense here, but it's just told to you so that when you come back to start playing with the system and in the future you start referring back to a system, you'll have it in the back of your mind. Okay, these are the different file systems. These are the different resources. These are what I could potentially use them for. Inside so as we've said, each node has these 128 processor cores. It's actually 2 AMD 64-core processors, and if you care, they're 7742s running at 2.25 gigahertz, but you probably don't care about that. By and large, most of the system has 256 gigabytes of memory per node, but there are 300 high memory nodes which have double that, so there's 512 gigabytes per node. Again, for data analytics work, this may be important to you. You may want to target these high memory nodes if you're doing large amounts of data processing or not. So this is what the inside of a node looked like. 2 processors, they're connected together by an interconnect inside the node, and then each processor is connected to the high performance network. Again, most of the time you don't care about this, but to make efficient use of a node, it's often worth making sure that you're using both processors, even if you're not requiring all 128 processors on the node. It's worthwhile spreading out your tasks across these processors to make sure you can use all these memory bandwidth, because each processor has a chunk of memory attached to it, and to make sure you get to use both of those network interfaces efficiently. So that's also, again, a lot of the time, this is detail you don't need to care about, but to get the best performance out of the system, particularly if you don't need all those 128 cores for your job, maybe you only need 64 cores, maybe you only need 32 cores, then making sure that you place those processors or those threads that you're running in the correct way will give you higher performance than, say, just running all 32 on the first processor and leaving the second processor empty. There's nothing to stop you running it in a slightly less efficient manner, but you'll get better performance and you'll get better use of the resources for your time and your budget if you understand a little bit of these details. There's a fairly large software stack installed on the system, so we're using the Cray Linux, HP Cray Linux environment, CLE, but that's not as arcane or bespoke as it used to be in the past. So in the past, if you went back 10 years, a lot of the operating systems on high performance computers like these would have been pretty niche or pretty specialized, and it would have been a big difference to the Linux that you're probably all used to running or interacting with in some way, be it local resources or university HPC systems and these kind of things. And nowadays, the Cray Linux is much closer to sort of vanilla generic Linux, so it's based on Scientific Linux 15. So you can take most programs onto it and compile things without too much of an issue. As we've already said, we use Slurm as a batch scheduler, so this is how we access data and the compute nodes and those data analytics nodes. And we have, by default, installed 3 different compiler stacks. The default one when you log onto the system is the Cray compilers, but we also have the GNU compilers, and I think we have GNU 10 and GNU 11 and possibly GNU 8 as well. And because these are AMD processors, we also have the AMD compilers. So again, there's a lot of detail here. Most of the time you don't care about this, but if you're porting new software to the system, a lot of software can have challenges being built with the Cray compilers, so you can just swap over to GNU compilers instead. Because it's a large-scale parallel system, we have the Cray MPI libraries and Cray communication libraries. So this is what we commonly use for parallel programming and using all those compute nodes together in a single application. And we have optimized versions of a range of scientific and numerical libraries installed. So the LibBLAS, LAPACK, SCALAPACK, these are mathematical linear algebra libraries, which are commonly used by a lot of applications to do things like matrix vector multiplications. We have FFT libraries, we have data format libraries like NetCDF and HDF5. We have Cray and we have Python and R already installed on the system, plus a lot more applications installed on the system, although that may not be applicable to data scientists particularly. And then there are parallel programming tools like debuggers and profilers available. And again, this may not be as much of interest to you if you're doing data analytics workflows where you're using Python or R, as it would be someone who's written their own C++ program or their own Fortran program and wants to bring it onto ARCHER2. So we have these login nodes, which what you first experience when you get onto Archer, and these are used for sort of compilation, submission of jobs, and general development work. There's these two data analytic nodes, which are used for longer running data movement, data pre-processing and post-processing tasks, although there's only a limited amount of resources. So I can't remember if I outline it here. Yes, I do. Okay, so there's limits onto how much of those you can use. And then the compute nodes are what are used for everything else. And the compute nodes are the main thing in the ARCHER2 system. The only thing to be aware of is using compute nodes requires a runtime budget. So resources on ARCHER2 are given out and constrained. So particular users get particular amount of CPU hours, for instance, or compute units we call them, and there's some match between compute units and CPU hours. And so if you want to run anything on ARCHER2, you need a budget with time in it, with compute units in it. Now for the course, you've been given an account with a certain amount of budget in it already, so you'll have enough budget to run the things we need for the course and to do some more small scale exploration. Beyond that, you need a proper project and a proper budget with larger amounts of resources in to use the system. Use of cores is restricted. What does this mean? Well, the login nodes have this idea of a fair share set up on them. So if you try and run, so we have 4 login nodes. We commonly have hundreds of people logged onto the system at any one time. So we can't allow any individual person to run large amounts of stuff on the login nodes because that just impacts everybody else's experience. So you can run things on the login nodes, but if you try and use more than a few cores or more than a certain percentage of a memory, you'll be restricted from doing that. So your things will run very slowly or will crash. So the login nodes are not designed for running large scale things. This is quite a nice setup in the sense that if you try and do something big, it impacts you, your job runs slowly or it crashes, but it doesn't impact everybody else on the login nodes, and that's what we're looking for. On the compute nodes, when we submit jobs, there is this concept of binding and placement enforcement. So again, this comes back to this idea here of wanting to put your workers, whatever they are, threads or processes, on particular cores on the processes we have here. And that means that there is some restriction on, you can't run, we've got 128 cores here, we can run up to 256 threads per node, but we can't run, you can't say try and run 1,000 things on the node because it just won't let you do that. And as I said, to make sure you get best performance, we need to make sure that we're putting things on cores correctly on the compute nodes. Otherwise, things will run, but they'll just run slowly. So that we have to be a little bit careful about that. Now, the way we do this on ARCHER2 is through the batch system called Slurm. And there's a lot of documentation on this online here through this website, through the ARCHER2 website documentation website, so that's worth having a look at. But basically, in general, we use batch scripts, which are a file where you write the requirements for your job. So this bit at the top here is all what my job's going to do, what do I need from the system, and then you can run your job inside that batch script down here. So here, this is a typical Slurm batch script for ARCHER2. I've given it a name. I've saying I want 2 compute nodes. I'm saying I want to use 128 cores per compute node. Or actually, I want to run 128 things per compute node. I'm specifying a partition. And in Slurm speak, this is like a queue. This is like a group of things to run on. So I'm using the standard partition. We'll look at what different partitions there are. And I'm also specifying a quality of service tag. I specify an account, which is my budget. So here I'm using Z19. I think you'll use TA06. Well, let me just check that. I should know off the top of my head what you're using for this course, because we change them between courses. That means some of the exercise material may be slightly out of date that you're going to do today. I don't always update the specific budgets between the course runs. So it may be that when we come and look at some of the exercise material and stuff like that, that needs to be updated. This again will become more evident when we come on to do it, so don't worry. So yes, okay, so you're TA065. So let me just make a change to that so it appears on these slides. If you were doing this, you would go your account here would be TA065. Has that updated? Yes, there you go. So you can see the account there is 065. In fact, actually, for most of you, if you've just got a single account on ARCHER2, you don't have to specify an account. It just picks up the default one. But it's worth having a look at anyway. And in fact, actually, well, I might be talking nonsense here, because it may be that you need to specify an actual budget in TA065. So let me just check what we've got going on here. No, it's okay. I think that's okay. I think you don't have individual budgets. It is possible to have individual budgets in the system. And then you would want to specify something specific for that TA065. Again, this is getting into too much detail for you here, but when we come back to do the practicals, this should make more sense. So what you can see here is I've specified I want 2 nodes. I want to run 128 tasks per node, and I want that to run for a maximum of 10 minutes. And what this time here is telling the batch system is, if this job hasn't finished itself after 10 minutes, you can kill it and then run something else there. So this is a maximum wall time. And then down here, I'm using the Slurm system to launch using srun my executable on 256 cores. And so that will actually use these resources I've asked for here. It's possible you don't have to have a single job running at once. So I can ask for 2 nodes. I still want 120 things to be able to run per node. But actually, I want to run multiple jobs, each here using only 64 cores. So I'm doing 4 lots of 64 core job starts. And because I've asked for 2 nodes, 128 cores per node, this will put the first 64 on the first processor, and the second 64 on the second processor, and then the third 64 on the second node first processor, and the fourth 64 on the second node second processor, and these will all run at the same time. If you are wanting to do this, and this is quite common for data analytics workflows where you want to run multiple things inside a single compute node, because a single compute node has got 128 cores, but you can't efficiently use all the cores for one job. You can do this. You can use these multiple srun commands to do this. You have to put the @ sign, the and sign at the end here, ampersand at the end here, and you have to put a wait at the end. And this is important, because if you don't put this wait here, if any one of these jobs finishes before the rest, it will cancel all the others, because it will automatically finish and the whole thing will shut down. So that's quite an important thing to do. But it is possible to run multiple tasks on the same node across. So here, I could have run these as 4 separate jobs, each using a node. But of course, that's not necessarily efficient, because I'm only using 64 cores per node. So I'm running it as a single job with 2 nodes and just running them all inside that. Or you can run a single job, and each you know, in there I can run 256 individual separate tasks, just like I'm doing here. So each one of these is a single core job, and I'm going to run 256 of them, and this does exactly the same kind of thing. Slurm also lets us do this thing called job arrays. So this is running multiple jobs now, but from a single script, from a single submission. And this is commonly useful if you have, you know, a single task where, for instance, you can fill up a whole node, but you want to run lots of different versions of that on different data sets. So for instance, if you have an application, it requires 2 nodes to run, but you need to run that application on 10,000 input files. Do the same thing each time, but on different input files. Then job arrays are a good way of doing this. Here we've specified each job is going to take at most 4 hours. I'm going to use 1 node and 128 things on that node. But I've got an array of 56 jobs that I'm going to run here. So I've said I want my array goes from 0 to 55, so it's 56 jobs. And each time it runs, it's going to run this line down here on a separate node for 4 hours. And so what it gives you is it gives you this, when it runs it, it gives you this task array ID, or array task ID. So each one of these is going to, you know, the first run's going to have a 0 and then a 1 here, and then 2 and 3 and 4 and 5 and 6. And then you yourself are going to have to implement some logic in your application to pick up that task array ID and then do something slightly different for each application, reading a different input file, those kind of things. So job arrays are a good way if you of submitting jobs if you've got large amounts of files to process and do exactly the same thing to do. Or if you've got an application where you want to run the same application many times but with slightly different parameters, a job array is a good way of doing that. Now, of course, you can do this yourself manually by just submitting the batch script, this batch script multiple times and changing it each time. But that's quite a lot of manual work for you. And it's also slightly less efficient from a batch scheduling side. If we can do it through the Slurm system like this, it knows it's got 56 tasks to do, and it can efficiently do them rather than you submit them as all separate tasks for it. Now that's the standard way we use Slurm. And actually, I haven't shown you how you run one of these, but you use a command called sbatch. And that sbatch command submits the batch file, this kind of file that you've written here, to the system. And that Slurm then picks that up, and then it will run that for you when it has free resources. And you'll get the output back once it's finished running, or during the run. Of course, there are times where you want a bit more of an interactive process, so you want to be able to try things directly. You don't want to submit stuff into a batch system and wait for it to come back. You want to try effectively running things directly on the compute nodes yourself. And Slurm also lets you do this. So there are interactive access patterns that you can use to get onto a system. There's confusingly in Slurm, there's 2 different ways of doing this. One is to run what we call an srun command, which you've already seen. It's the thing we use inside the batch script down here, which launches our jobs on the compute nodes. But you use the srun command directly from the login node yourself, and you want to specify exactly what you want to do, and it will run that command directly for you here. So we've got an example here. On the login nodes, I would run srun, ask for 1 node. I only want 2 tasks on that node for whatever reason. I'm saying I want to submit it to the short queue, and this is important because that's likely to give you a quick turnaround and your job will start and away it goes. And this is, I want it to run for 20 minutes at most, and this is what I want to run. It will run this Python program for me. And so this is taking an application and run it in it interactively for me. And then once it runs, I can start to see the output coming up on my login screen, see what's going on. if I want to do this, actually I want to log directly into the compute nodes myself and then run commands myself rather than telling it what command I want to run, then I can use this command here. So it's exactly the same thing, but instead of saying I want to run Python with a program, I actually do this thing here, --pty bin bash, and that gives me a login terminal to a compute node once it starts, where I can run my commands directly. Now, of course, this is not the way that it's sensible to try and run long jobs or large jobs, because you have to have that terminal open all the time, and if the terminal closes, your job crashes. So if you're wanting to run your production jobs, then of course this batch system way where you submit the job and it's run for you is the correct way of doing things. But interactive use can be very useful for debugging problems or for developing applications and checking things out. So we can use the srun command directly. We can also, there's also a way of doing this, which is actually what srun does itself directly, but you can separate this out. You can use what's called salloc, so which allocates you resources. So you can ask for a set of resources. So like here, salloc, I want 8 nodes, 128 tasks per node for 20 minutes. That goes off. When the allocation is ready, it comes back to you. And then that means that anything you then run from the compute nodes will run inside that allocation, so that you can then do multiple srun commands inside the login node, and that will launch it onto those compute nodes you've had as well. So that's also a way of doing it. srun itself, if you call it directly from the login nodes, will do its own salloc and then do the srun after it. So it just sort of wraps this process up for you. But you can separate it out, if you want to ask for a set of nodes and then launch different commands on those set of nodes from the login nodes. That's possible. The only thing to remember, of course, is that just like with the general batch jobs, you don't have access to home file system on the compute nodes. So if you're trying to do any of this interactive stuff, you need to do it from the work file system. Otherwise, you're going to have problems. Okay, so we have a reasonably complicated, it's not really actually, but we have a range of different queues and quality of service, a range of different partitions and quality of service setups available on ARCHER2 for different jobs. So you'll see back here that quite often I'm using this partition equals standard, QoS equals short. For this one down here, I used partition equals standard, QoS equals standard. So what do these things refer to? Well, they basically sort of specify how many nodes you can ask for, how long a job can run for, and how many jobs you can run at any one time. And that's specified by a combination of partition and QoS flags to a batch system. So for most jobs on ARCHER2, the maximum runtime is, so standard jobs, a job on a standard partition with a standard quality of service, maximum runtime is 24 hours. You can have at most 1,024 nodes in a single job. You can have 64 jobs queued and waiting to run, and you can have, of those, at most 16 jobs running at any one time. And there's a slight further caveat: you can have a maximum 1,024 nodes being used by any one user at any one time. So if you had 1,024 node jobs, you couldn't have 16 of those running at any one time. And this is configured like this because we want, we have lots of users and we need to be able to share the system fairly between users. So we don't let users run particularly for too long on any given job, and we don't let users use too many nodes on any given job by default, because otherwise it's hard to share the system efficiently with other users. There is a couple of variations on that. So there's a similar one, but so this standard queue runs across the whole system, and you can get nodes in there which are standard memory nodes, i.e. 256 gigabytes per node, or you can get nodes in there which are 512 gigabytes per node. And if you don't specify, you just get whatever comes. If you remember, I said earlier on, there are 300 high memory nodes with 512 gigabytes, and the rest have 256 gigabytes. If you know you have specific requirement for these 512 gigabyte nodes, then you can specify that as a QoS in a partition, and you can submit your jobs to that. Because there's only 300 of those nodes, you can't ask for 1024 nodes at once. But other than that, you're pretty similar to a standard queue. There is also what's called a task farm quality of service. And this lets people submit large number of jobs, but for a smaller number of nodes. So if people want to have large, the idea here is people have got lots of small jobs to run at once. So they're not going to be asking for large numbers of nodes, but they want to be able to run more than 16 at a time, and they want to be able to queue up more than 64 at a time. There's a slightly reduced, slightly eased set of jobs queues and jobs running requirements for a task farm QoS. The one we'll be using today, and the one that's good for debugging and development work, is the short queue. In the short queue, you can run up to 32 nodes for up to 20 minutes, and you can only have 4 jobs running at once as a user. But the nice thing about this is the turnaround on that is pretty quick, so you can effectively get your jobs to run instantly on there if you're doing debugging, if you want to try out practical examples. And so that's what we're going to be using today. Most of these queues up here, you submit your job and it runs at some point in the future. The short queue runs pretty quickly. And then there is a long queue for people who want to run for longer than 48 hours, for 24 hours. So we can run up to 48 hours. I notice this is slightly wrong here. That should be 512. So there is a 48-hour queue as well, and you have to specify it as a long queue. Let me just, whilst I remember that, let me just fix that mistake in my slides. Pretty sure that should be 512. And then there are some other ones, other queues as well. So there's a large scale queue. So as should be evident here, the standard setup that most people use doesn't let you use more than 1024 nodes at once. But it is possible to use a full system, use all 5,860 nodes, just using this large scale quality of service thing. There's a restriction on how much that can be used, because it impacts other users, but you can do it. You can run up to a much larger number of nodes than 1024. There's a low priority queue for jobs that will, not guaranteed to run anytime soon, but you don't get charged to run them. So it doesn't cost you anything to use a low priority queue, but they only run when the system is quiet. And then there's this serial queue, which is the way we access that data analytic nodes, those data processing nodes, where you can run up to 32 cores for up to 24 hours, and you can only have 4 jobs running at once. But this is not charged either, and this is the place where we can download data or upload data or do any of those kind of tasks. Again, I know there's a lot of detail here. I don't expect you to remember this all, but it's worth knowing that these are the things which configure how you can use the resources and what resources you have access to. And these are the things which you can change yourself to submit jobs to different things. Okay, I see I'm already running over my timetable quite nicely, but we'll get there. We've not got that many more slides here, and then we can go on to a practical example. As I've said already, if you have any questions as we're going along, please do let me know. Otherwise, I will just keep talking. So let's have a look. Now, one of the things we've already discussed is this concept of placement and efficiently using the hardware. So we've already looked at this in a little bit detail, but this is a more abstract view of what an ARCHER2 compute node looks like. We actually have quite complicated hardware setup inside. We have the two processors connected together. Each processor is connected to a networking interconnect. But inside each processor, we don't just have 64 cores. We have these groups of eight cores grouped together into 16 cores, together into 64 cores, etc., etc. Now, most of the time, you don't care about this. You don't care what's going on here. The times where I think it does make sense are these things where we want to, okay, I don't want to use all 128 cores on my node because I can't use all that in my parallelism, or I need more memory per processor or worker than I can get if I use 128 cores per node. And in that case, we want to make sure in general that we spread out our workers across the node so we get access to all these fast memory connections, and we get access to these network connections. So instead of, if I only wanted to use 16 tasks per node, by default, it would put them all on this first block here, and then all these memory connections here I can use, but I have to go through the other blocks to get to them, and that slows things down. And if I want to use the memory on this other processor, I have to go through this interconnect in the middle, and that slows things down again. Whereas if I actually put, 2 tasks per block here, then I'm spreading out my work across all the different resource partitions, or what we call NUMA nodes, NUMA regions, but you don't need to worry about what that means. There's much more detail here on the hardware guide online. It just means I get access to all these fast connections directly, and I'll get better performance that way. So as we've seen before, we specified in some of my other examples, 2 nodes, 128 tasks per node, and that will, by default, assign a worker to each core individually, starting at the first core on the first node and going all the way up to the last core on the last node. And if I only asked, if I here said srun minus n 1 to 8, even though I've asked for 2 nodes in my batch job, it would only ever use 1 node and it wouldn't go on to the second node. Okay, so that's, a coarse example of the kind of inefficiency you could get. If I ask for 2 nodes, but I only run 128 things in this configuration, it would only ever use 1 node, and the other node would sit there doing nothing. Now I can get around that by specifying a bit more detail in my batch script here. So I said 2 nodes. Now I only want 64 tasks per node, and I want to do 2 CPUs per task. Okay, and so that means that 2 CPUs per task gives me 2 of these blue blocks per worker, and then that automatically spreads me out so that my first 4 workers are here, my second 4 workers are here, my third 4 workers are here, rather than squishing them all onto the first 32 cores on the node. And so that's the way I can specify how I want to spread my workers. I'll do my placement of my workers across those kind of things there. And so we do have the control for the batch system to decide and enforce how we do this kind of spreading out of workers to hardware. And this can be important, particularly for scenarios where you're not using all the cores in the node. You can actually go, so that's what you want to do if you are submitting, if you're submitting different jobs, if you're submitting a single job, which you're going to use all those cores. If we're going to then combine that with running multiple jobs inside a single batch script, it gets a bit more complicated. But it is possible, and there's more detail in this on the ARCHER2 documentation, to manually specify how we parcel up cores to workers from different jobs and spread those out. So there are tools available to do this. If that's the kind of work pattern and workflow you have, then it's worth spending a bit of time looking at how you do this. Okay. So that's the compute side of things and submitting jobs to the compute side of things. The other part of the system which can have variable performance impacts for your places where you can optimize or damage the performance of your applications are on the file system side. So as you'll recall, we've already discussed that at the moment, the main high performance file system is this work file system. It's something called a Lustre file system. So Lustre is a large scale parallel file system. And it's set up to provide high bandwidth for large parallel jobs. So this means you can read and write large amounts of data. And I think on ARCHER2, I've benchmarked up to about 80 gigabytes a second read and write of data. So you can pull in large amounts of data, or you can push out large amounts of data if you're using sufficient number of nodes. Lustre is quite complicated, but from a user perspective, there's not much you need to worry about. What you do care about somewhat are the sort of two different aspects of a file system. One is what we call metadata. And so metadata is really directory structures, file names, and file permissions. And then the other one is the data storage, where actually Lustre takes your files and it can split it up across different storage devices to spread out your file and give you access to more I/O bandwidth. This is all configured on Lustre through something called striping. So in Lustre, you can specify your file stripes. Now, if you have one single file, which is accessed by lots of workers at once, individually, then striping is a great thing because you can split up that file across lots of different devices, and each of the workers can access its part of the file separately, and that's where you get your I/O bandwidth, your high performance from a file system. However, striping has an overhead. So if each file is only ever accessed by one worker, then striping it across different resources is not going to help you, and in fact, it will increase some of the overheads of looking at that file and getting the data out of it. So what we do on ARCHER2 by default is that all files are not striped. So all files are just on a single storage device. But if you want to in the future, when you do stuff, you can change the striping so that you can stripe things. Now, for a lot of data science stuff, where actually what you generally have is a large number of files rather than one big file that everybody accesses. This setup with no striping is the optimal setup. It's sort of the optimal way of doing things. But striping does help improve overall bandwidth and performance if you are accessing files in parallel. If lots of workers are accessing the same file, then that can be a way of doing it. So if you are wanting to change the stripe, you use this command called LFS. And LFS, let me see if I can demonstrate this. Let me just get an ARCHER2 window up to make it make more detail and more sense. But give me a second. Just changing the font size so you can see it. There we go. Right, let me just share this terminal window instead. Okay, so this is, hopefully you can see this. It's not come through yet, it's just coming through now. There we go. So this is my terminal on ARCHER2. You can see when we've logged in by default, I'm not using a project account, the course account here, but I'm using my own personal one. You can see we've logged in by default here to this home file system. And this is one I said, you can do lots of stuff here, it's backed up, that's fine, but it's the one that's not accessible on the compute node. So let's go over to this work file system. I'm now on the work file system, and I've got lots of stuff in here. Most of it's nonsense. But this work file system is a Lustre file system, and we can see actually using this command here, we've got this Lustre file system. Look at what's available on the disk here. You can see the Lustre file system, actually we have multiple ones of them. This one here is work 3, and you can see it has these 12 different workers, 12 different what we call OSTs. These are the things that the data can be split up across. And it also has 2 metadata workers as well. Actually, we can see there's 3 of these work file systems. Each project is on one of the work file systems. So you can see here we've got 12 workers we could stripe our files across. But if I create a standard file, so if I just create a file called my file, and if I do an LFS get stripe on my file, you can see that its stripe count has been 1, and then it gives you some other details here, but it's not hugely important what those details are. The LFS, the Lustre striping, is set on directory level, so a file inherits the striping which is set by default on the directory, and your directories will be default set to striping to will be set to 1. If I create a directory and I look at the stripe on that directory, it's got a stripe of 1, but I can also use this command lfs set stripe -c -1 striped. And what I can say here is Lustre set the stripe of this directory, so the number of things that it's striped across, to be -1. That means use all the maximum, all the things available. And we'll see here it's got a -1 stripe here. So if I now create a file inside there, inside that directory, and I check what it is, we can see now actually that directory file, my file, has now got a stripe count of 12, and it's been split up across all those file system workers that we had available. And so that's the way I can, if I was going to use this file in parallel, get higher performance out of that. But of course, you can imagine if I'm using this file from a single worker, then it's a lot of work to go and find the individual chunks of this file and go and look up that data. So that's the Lustre file system. Now again, you may think, well, this is a lot of detail. Do I need all this detail? This is all very abstract. I'm maybe not going to do any of this stuff anyway. Again, this is just information we're giving you, like the placement and binding information. Those are the 2 things where they can have a sort of direct impact on your application performance. So how you structure your files and access your files on a parallel file system can impact how quickly you can get your data and how quickly you can read and write your data from your applications, which in turn will affect how quick your application is, or how efficiently you're using the system, and how efficiently you use the cores that are available to you has the same impact. Now, for a lot of users, a lot of applications, they can just use the defaults which we provide on the system, and that's sort of the optimal way of doing it for their jobs. But for some users, that's not correct, and we often experience for a lot of the data science workflows that's not correct, because there's a lot of use cases where, for instance, we have large amounts of small files, or we have large amounts of files to process, or we have workflows where you can't use all the cores in a single node. And so these are the things that we want to highlight here for this course, because when you come to actually run your R or your Python or whatever it is you're going to be using, that's the point where you need to think, okay, how do I set up my batch script for my job? What do I need to care about? What files am I going to use? Where do I place them? And how do I configure them to get the best performance? So that's why we flag up these 2 things in introductory lecture. Of course, there's lots more stuff you could look at on ARCHER2. There's lots of information on how you optimize performance through compilation and compilers and mappers and those kind of things. But that's not generally how data scientists tend to use a system like this. And so that's why we're focused on these particular bits of hardware. So in summary, so the ARCHER2 basic hardware usage is pretty straightforward, and for what it's designed for, which is large-scale parallel jobs, the defaults are usually fine and will give you reasonable performance. Running lots of small jobs or serial jobs together, which is much more common in data analytics and data science workflows, is possible, and we can use combined S-runs or array jobs to do that, as we've already seen. But making sure we data process placement and thread binding, so we're using those cores efficiently and we're spreading out across workers, across cores, is going to be important to make sure you get the best performance. And as we say, file system configuration may be important for your use case. For most people here, I would imagine that the default Lustre setup is going to be fine and you don't need to do anything there, but it's worth considering whether there are things you can do to improve your Lustre performance there. And when our solid state storage file system is available to users later in the year, that's something that it's definitely worth considering for data science workflows, because it will give much higher performance for that file system as well. So really, ARCHER2 is complicated but simple for a lot of users. Considering your specific use case or your specific workflow and how to make it work efficiently on the hardware we have and the configuration we have is what's important to make sure we're using ARCHER2 efficiently. Right, any questions off the back of that? Now, I appreciate, again, it is pretty abstract until you actually get your hands on the system and try and do some work. But any questions on that before we start? So striping can be efficient for large multiple files. Dave, it really depends. Whether striping is efficient or not really depends on how you access the files rather than the size, particularly the size of the files. And of course, I didn't really cover it in detail, but the default striping size in Lustre is 1 megabyte. You can change that, but it splits the file up in chunks of 1 megabyte. So if your files are smaller than 1 megabyte, then of course striping is not going to help you anyway. But for striping to be useful for you, it's about how you access it. For striping to be useful, you need multiple workers to be accessing that file at the same time or similar times for the striping to be beneficial. Otherwise, you're just making the same worker go and ask where the next stripe is and where the next stripe is, and that's just overhead. Now, of course, that's the use case for parallel programming. We do parallel I/O. You have 10,000 workers, but they can all read and write chunks of the same file, and that's where striping comes in. For a lot of data analytics or data science stuff, that's not commonly what's done. But if you're using libraries like HDF5, NetCDF, Adios, these sort of I/O libraries, then they do some parallel I/O, and then striping would be beneficial for you. Any other questions? Right, so I've already, of course, blown away my timetable a little bit. What I suggest is we take a break now, if that's okay. We take a break now. Fortunately, there are points where we can catch up on this. Particularly the next lecture shouldn't take as long as I have on the timetable. But if we take a break now, and if we come back at 11:40. We'll have a little play on Archer, and then we'll talk about installing software and containers. So if that's okay, I will see you back here at 11:40. If you're okay and you don't want to go away and you're quite happy just to try out the exercise now, which I'm not suggesting you have to do. Breaks are important. Then what we're going to be doing when we come back is we're going to be going to the GitHub for this course, and we're going to go have a look at practical 1 exercise sheet. This is getting to know Archer. This is log on, check you can do things, and then run some test jobs, run using an existing program on the system here. So hopefully it's all pretty well outlined in the practical handout, but if you have any problems getting onto the system, then it's worth dropping a message in here and we can help you out with that. And you'll see in here that I have not updated it. It said TA, it says TA055. You just need to change that into TA065 when you're doing nothing. But as I say, feel free to not do that now, have a break, come back and we'll do that at 20 to 12. Okay, so hopefully what you're working through now at the moment is this exercise sheet 1, practical 1. So if we go to the GitHub, the Archer, EPCC Ed, ARCHER2 Data Science, GitHub, you go to exercises and then practical 1. And you'll see there's a login onto ARCHER2. You can change TA055 to TA065. And then this is sort of just run a sample job to get you up and running on the work file system. Download this repository that we're looking at here. Play around a little bit with how you say run different configurations of processes and threads, so different workers. Will do, yep. I'll put the link in. I'll put it in the course Etherpad as well, but that's where we're going. So look at that placement and binding, playing around a little bit with that, as we said. So I've not gone into detail, but you know, each program you run, we would call a process. Processes, programs that run, can have their own workers, which we call threads. And so, you know, individual programs can have little workers running next to them, and there we generally want them to run on cores which are close to those workers, and so that's why we want to control these different bindings. And the nice thing about this example that you run here is we use this program called XTHI, and that will print out where every individual worker is running, so you can see how many cores are being used and which cores are being used, and so that can give you a handle for that. And then we can also run this existing program called streams, which calculates how much memory bandwidth your cores can get, which is obviously important for a lot of applications to get good performance. And you can play around with the different placements to see what happens there if you get the placement wrong, and those kind of things, just to give you a feel. So here we're just taking existing applications and running them and just having a feel for what ARCHER2 is like. So please do give that a go, and then let us know if you have any issues or if you have any questions about it. And we'll start the next lecture at 12. Okay, hopefully you've had a chance to play with ARCHER2 and had a look at how you submit jobs, how you get onto a work file system, and what standard sort of process placement looks like for a job. As I say, for a lot of you, you may not need to get into this level of detail, but it's worth knowing that this detail is here and it can impact your job performance. So I'll just share my screen to show some examples of this. Hopefully you'll have seen the same stuff yourselves. Let me share the screen, share application. So I'm in the streams benchmark here, which is pretty standard benchmark of memory bandwidth at some level. And this is running 128 cores on the node. What we can see is we're using 128 workers, and we can get somewhere between 200 and 220 gigabytes a second of data of memory bandwidth. Now, what specifically that means is a little bit complicated. You know, each of the benchmarks are slightly different, and there's read and write bandwidth in there. But that's what we can sort of get, about 220 gigabytes a second at maximum, which is good. This is what each worker was getting on average. So if you times, you know, 1.7 gigabytes a second by 128, you should get to around 220 gigabytes a second. And for most applications, if that's what you're doing, that's fine. Of course, if you then try and underpopulate, so use less workers, and here's an example where I used only 64 workers, you can see what's happened here is in my default way of using those 64 workers, actually I've got about half the memory bandwidth of a node, so I'm using less workers and I'm getting half the memory bandwidth. I'm using half the number of workers, I'm getting half the memory bandwidth, which sounds fair, but in reality, actually, we should be able to get the whole memory bandwidth of a node for a reduced number of workers. We shouldn't have to use all the cores to do that. And what's happening here, of course, is if I ran my XTHI example on that, which I think I did here, you can see what it's doing is I'm running 64 workers, and it's putting them on core rank 0 up to 64, but it never uses up to 63, sorry. It never uses the next, so that's all on one processor in the node, not two processors. It never uses the second processor, so we only get the memory bandwidth from one processor, not from both of them. And that's why our performance is half the memory bandwidth for node, which can have a big impact on your application performance because most applications are memory bandwidth limited. If I set it up using my batch script in a slightly different way, where I spread them out, so the first worker has the first 2 cores and the second worker has the second 2 cores, etc., etc., you can see we go all the way up to 127 cores. We're using all the cores. We still only have 64 workers, but again, we're getting that 220 gigabytes a second. And actually, you can see here we're getting slightly better performance here. Actually, underpopulating using slightly less workers, we can get a slightly higher memory bandwidth than if we had all the workers, all the cores working at once, because there's a bit more contention in that case. So making sure that you configure your batch script to do that efficiently is important. And the magic I had to do there was I had to specify I want 64 tasks per node, 2 CPUs per task. You also, in this scenario, have to add in another one, which is to say only use one thing per physical core to get my output like that. Otherwise, it actually tries. So I haven't got into detail here, but there are actually 128 physical cores on the node, but each physical core can run 2 things at once. They're what we call hyperthreads. And if you don't tell it to only use 1 thread per core, it tries to use those hyperthreads, and so it still doesn't spread you out. So you can specify just these 2 without specifying this one, and you'll still not get that high performance. And that's why a tool like XTHI is quite nice, because you can actually test what your batch script will do before you run it on your actual application and see how you're spreading your processes out across the node. Any questions about that? Okay, so we'll go on to the next lecture then. So, we could run this course in a different way. We could start off with Python and R and then come back and look at the hardware. I chose to run it where we look at the hardware first and go into the detail there and then talk about the software after that. It possibly makes it a little bit more difficult, a little bit more convoluted to understand what's going on to start with, but hopefully once we start looking at the software side of things, particularly in Python and R, some of these more technical details we've been going through will make a bit more sense. Anyway, so we've looked at hardware and the kind of hardware which is probably important to data science workflows and applications on ARCHER2 in terms of giving configuration to performance. Of course, the other part of it that's of critical importance for anybody using ARCHER2 is the software side of it, and particularly how you build software efficiently and how you what software is available and these kind of things. So as we've already been through, Archer has a lot of software already installed. It's primarily mostly focused at computational simulation. So there may be a lot of things there which are not of interest to data science workers. But particularly there are two optimized packages that are important. One is a version of Python, Python 3.8.5, so it's not the most up-to-date Python, although newer versions will come. But it's optimized for the system, so it's built with optimal or as optimal as possible maths libraries and things like that, and we'll come on to that. And there's a version of R which is built in a similar way, R version 4.0.3. Okay. Now again, I will just do a quick demonstration of. I wish it was slightly easier to switch windows in this without having to completely shut things down. Anyway, just to give you a flavor, we use this modular environment. It's pretty common across Linux shared systems like this. I can see what modules I have loaded by default when I log in by using this command called module list. So these are all things that are loaded up for me by default. Particularly the programming environment is what sets up compilers, and so by default I have the Cray programming environment set up. That's what you get when you log in by default, but you can change that. You can have a look at what modules are available, what software is centrally installed for people by using this module available command, and you can see there's things like matplotlib, netcdf, pytorch, seaborn, TensorFlow. Then we have scientific libraries like Eigen, GSL, MKL, FFTW, it's not in there, those kind of things, scientific libraries. Then we have actual applications, and these are all the computational simulation ones, usually. And then other sort of supporting software. So we have GNUplot and ParaView, visualization, stuff like that. And then we have optimized versions of things that Cray provides, so the IO libraries, MPI communication libraries, FFTW, so that's fast Fourier transforms, those kind of things. So you can see there's a bunch of things already available, including, as I've just pointed out, the Cray Python setup. So actually there is also, the default is Python 3.8.5. There is also 3.9.4.1 available, which you can switch to if you need slightly newer version of Python. And then there's Cray R, as I said, the default is 4.0.3, but there's also 4.1.1 as well, if you wanted. And so I can do module load Cray. So let me just demonstrate this here. Clear. If I say which Python, actually I've got my own Anaconda set up here, which is not very helpful for this course. You can do that as well yourself. You can install your own Anaconda. But if I do module load Cray Python, you can see that module load is set up so that now I get that create Python install there. And if I wanted that slightly newer version of Python, so if we go Python, that will say it's Python 3.8.5. If I wanted that slightly newer version of Python, I could use a module system to get that as well. I just have to be a bit more specific when I load it so I don't get the default. So I do 3.9.5.1. And then if I go Python now, you can see it's a slightly different version of Python I've been given here. And the same for the R or any other packages you use on ARCHER2 using the module system. Okay, so that's all well and good, and we have compilers and those kind of things. The two challenges to installing software, your own packages, other things you need on ARCHER2 are Cray Linux is not, it's not that far away from standard Linux, but it's not Ubuntu or whatever it is that people often develop data analytics workflows on top of. So it may be slightly different, and so we may not have all the dependency libraries installed. You don't have sudo access. You can't just do a yum or an apt install of things. And so that can be challenging for users bringing particularly data science workflows across. And the other thing, of course, is this file system thing can mess things up a little bit, because we don't have that. We don't have that home file system available on the compute nodes, and most of the time you're going to be wanting to run things in the compute nodes. When you try and install things by default, they install on the home file system, and then you don't get them on the compute, the work file system. So we have to. There are a couple of ways we can get around these kind of things. If we have things where we need large amounts of dependencies installed because your application or the program you're using, the package you're using is built on something like Ubuntu or expects a whole bunch of things to be installed, then we can use containers and containers like Docker to actually run a prepackaged operating system with all the things in for you, instead of you having to install all those things manually yourself in your home directory or your work directory on ARCHER2. And there are ways we can specify when we install things not to install in the home directory, but install on work instead. Okay, so I've already shown you there's lots of things available on ARCHER2. One of the important things are the maths libraries. So Cray libsci provides linear algebra libraries, which again, most of you data science users probably don't have to care about, except things like Python and R, or particularly NumPy and R, or SciPy and R, will actually, to get good performance, build on top of these kind of libraries. So they compile and use numerical libraries under the hood, and libsci, Cray libsci is the one we have on ARCHER2 to provide that functionality. And that's why we have these Cray installed, Cray Python and Cray R, because they have some of this stuff already built in, so they're already using Cray libsci, so they're already calling the targeted maths libraries that are optimized for the system. If you're interested in any of these things, there's a lot more maths libraries available, and you can have a look in a lot more detail about what these maths libraries actually do and what functions are in there. Most of the time, this is just handled for you. As we've already mentioned, for these programming environments which set up the compilers for us, and just as we saw before, we can swap between them. So I'll give you another quick demonstration of that. Apologies if this is all obvious, but sometimes I think it can be a little bit confusing. Yeah. So as I said before, we have this. Currently, I've got this Cray programming environment set up, which gives me the Cray compilers by default. Now in ARCHER2, these are wrapped up in what we call compiler wrappers, called CC for C compiler, capital C for the C++ compiler, and FTN for the Fortran compiler. And you can do, if I do CC minus V, we're using the Cray Clang C compiler version 11 point something. If I do the capital C, you can see that it's exactly the same but for C++. And if I use ftn-v, we can see it doesn't like that, and it's probably, yeah, capital V. You can see it's a Cray Fortran compiler. However, we have other compilers available, as I've already mentioned. So we have this module avail prog env. We have the Cray, the GNU, and the AMD compilers available. So if I did module load prog env GNU instead, and then now I try cc-v, you can see using the same compiler wrapper, the same CC compiler, I'm now getting the GCC compiler, not the Cray compiler. And likewise, if I do cc-v, I'm getting the GCC compiler again. And if I do ftn-v, I'm getting the GCC version of Fortran as well. Okay, so we have these different compilers and they're already provided for you. So you don't have to do things like GCC, G++ to do compilation. You do CC or CC, capital C to do your compilation. And you swap the programming environments around to get the correct compilers. And that's all done on purpose so that things like the communication libraries and the scientific libraries are all configured for you when you swap a programming environment around. You don't have to set up all the libraries yourself. Again, if you're just using Python and R, a lot of the time you don't care about this, but quite often you may want to install a new Python package, a new R package, and they may involve some compilation. They may not just install by default. You may not just be able to pip install some things on the Archer system or whatever it is you use, and cran install. So you may have to build some source code, and this is where this knowledge becomes useful. As we've already said as well, the thing to be aware of is that if we're building stuff that's going to be used in the compute nodes, we need to build that software on the work file system. That's the only one that's available in the compute nodes. So, for example, if I wanted to do this for Python, I could load the Cray Python module, and then I can use this special command, export Python user base, and then specify somewhere on my work directory. And if I do this, any Python installs that I do will then actually go into my work directory rather than my home directory. And then I can use them as default just by exporting this Python user base environment variable. It's possible on ARCHER2 to use virtual environments as well. So we can set up a virtual environment on ARCHER2 inside which you can use pip or conda to install the software, as long as we've set this Python user base first to make sure it's on the work file system. You can use the pip commands generally as normal. We have to use --user because we can't install as a root user here, so that kind of thing. So that will definitely help you with the Python side of things if you're installing your own Python stuff and getting things installed on the work file system instead. Sometimes if you're installing things like pip install or building your own stuff, you have to set up what compilers the installer should use, and you may have to run these commands as well. The same thing is also true of R. So export, in this case, r_libs_user to a directory on your work file system. And then inside R, you can do the installation as normal, and it will build it and put it inside the work file system. And so when you come and use that, as long as you export this environment variable, then that will get you up and running with that. If you're having to build some more complicated packages on ARCHER2, then sometimes you have to create an R preference directory, and this is on the home file system. So you create this directory called .R. You create a file there called make_vars, and you add the same thing in there. And then that can let you build things locally if there's some certain things where you can't just install them as install.packages like this. Then that will let you build these things locally. So that's the sort of examples of if you're installing pretty standard Python or R software, most of the time it will work. You just need to ensure you're installing it in the correct place, not in your home directory where it will go by default. And you need to sometimes configure the compilers so that the package managers know what to build, and generally you want the GNU compilers built loaded, because that's what things will build easiest with, or have been built with before. And again, this should make more sense when we do some of the practical sessions. But as an example now, I can show you what the R thing looks like. So let me share a different screen again. Yeah, okay. So I've done my module load create, and then if I go in here, this is just on the login nodes, and then if I do I'll get the syntax for this wrong. Oh, no, right first time, it's unusual. You can see that the default R install from Cray comes with a bunch of things. It comes with a bunch of libraries already installed that are already in there for you. And it will tell you all about what's there. But if you needed to actually install your own things, which I have done for this course before, I can do this export rlibs equals user. And you can see I have a directory in my work file system here where I have a bunch of things that have been installed into it. So now if I go into R and do the always get it wrong. Do the install.packages here, then we've got some more things that have come in here that we didn't have in that list before. Snow and snowfall, RMPI, parallelly, data table. These kind of things have all been installed in my local directory, which are not part of the standard thing that comes along. And you can see at the top here, I've got these set of packages here that have been built, which I've put on my work file system. This opt file system where Cray Python and Cray R installed is also available on the compute nodes, but it's not somewhere we can install stuff. Okay. Back to the lecture. So that's all well and good for those kind of things which you can install by default. And these are kind of things. If you need to compile some more complicated software which you can't get through something like Python, something like R, those kind of things, then what we can use, and you try and install it on, and build it and install it on ARCHER2, but there's lots of things missing, lots of libraries missing that it needs. What we can use, and what is commonly used in a lot of places now, are containers. So Docker is a good example of a container system where Docker images are sort of the files and directories that a container is produced from, and then you build a container which is a runtime image or a lightweight virtual machine, and then you can run that. And effectively what you do is you're running your own operating system on top of the host operating system with all the things you need installed in it directly already. And that lets you get around some of these problems. And the nice thing about this is, of course, there's lots of default containers available out there for you, particularly on things like the Docker Hub, which already have things installed in which you can just pull and use. Now, of course, there's some challenges here because all these default containers generally won't be built for things like the high performance network, which we have on ARCHER2, and so there's some challenges around that. Although for a lot of the data science work, you're not doing parallel programming, so you can ignore some of those things. But containers are a way of running a sort of specialized operating system on top of what we already have on ARCHER2, where you can install your own applications inside, or you can use pre-built operating systems which already have the things in you need installed. We don't use Docker on ARCHER2 because Docker historically and possibly even still has some, the way it works has some security implications when you're running on a shared system like ARCHER2, where other users can be running at the same time. So we actually use a different container system, which is quite like Docker, but designed more for high performance computing. There are a few of them around, Shifter, Charlie Cloud, things like that, but we're using one called Singularity. Now, it's a little bit complicated what version of Singularity we're using, but the ARCHER2 website has reasonable documentations on it. So we have this Singularity container system on ARCHER2, but it can run Docker containers, which is a nice thing. So Singularity lets you pull a container, say from the Docker website, and then run. So that pulls down the sort of host thing to run, and then you can run commands inside it like this. So we can do Singularity run, name of the container, and then you can just run this command. And there are also data sets, containers out there and other places which you can also use. So you can have a look for the kind of containers that you may want to use there, where we can just pull and run those kind of things. So an easy way of doing this to play around with it would be to do Singularity pull hello world from this container site and then run that on ARCHER2. Now, actually, Singularity gives you lots of flexibility in what you can do. There are ways to just run the container as it comes with the default functionality in it, and containers generally have a default run script when you use them. You can run the container and get a shell, so a sort of a bash, a terminal where you can type stuff inside the container and do your own manual things, or you can run a container where you execute a specific command that you want it to do at the end there. Once you have a container, you can play around with it. So Singularity lets you inspect what's inside the container and sort of the default command and those kind of things. And we have a bunch of containers already built on ARCHER2, Singularity containers for you to be able to use. By default, Singularity is configured so that it brings in your username and groups from the host system. And that means that you can access files and directories and packages that you can access as a normal user on ARCHER2. You do need to bring in a file system though, because by default Singularity will only try and mount your home file system. Of course, we know on ARCHER2 that home file system is not visible from the compute nodes. So if you want to use this container on the compute nodes, that's going to work, not going to work. So you need to do this binding flag here to bind and bring in additional directories. So here's an example here where I've got Singularity shell. So it's going to create me a terminal using a hello world container, but I'm going to bind the work file system in there. And that means I can go in and access anything inside that work file system from inside my container. I can also, so if I go in there, I'd have to go to cd/work z19 z19 Adrian J to get to it. But I can also, if I want to, rename directories when I import them into my container, and so I can call it a different thing as well. And this is a sort of a basic way to take a software environment and just get it up and running and used on ARCHER2. So you can then run them on the back end of ARCHER2 as long as you have the container, this CIF file, on your work file system somewhere. You can then just run the container, and that will take the application and run it on the back end. Now, this is easy inside a single node. As I said before, if you want to use the MPI, the high performance communication library and network between different nodes, if you wanted to run like an MPI job where we run multiple tasks, all collaborating on the same bit of work across many nodes, you need to be a little bit more careful, and there are ways that we need to do that. And this looks complicated. You don't have to understand it all, but basically, if you wanted to run like a single container using 256 cores in that single container, then what you would have to do is specify some of these special environment variables and flags when you run it. And what this is doing is setting up the libraries so that the communication libraries are picked up by the container, and it can communicate nicely with the network. And so it's a little bit more complicated, but really you just have to copy and paste this stuff into your script, and away you go. And there's an example of doing that here with one of the containers we have already pre-compiled for your Archer is one that does MPI benchmarking, so network benchmarking, which you can do there. It's also possible to, in exactly the same way as we saw with the batch system doing interactive jobs, you can also do these sort of things where you create a interactive session where you run the container from the login node but on a compute node, and it looks exactly the same as we had before. We just do this S run on the login node and we specify all the batch system information here, and then after that we just pass in our Singularity runtime information as well. And so, you know, and we can also run the containers on the login node as long as they're not doing heavy amounts of work. So here we can do a Singularity run to do a compilation of something from inside the container on the login nodes, and that will also work as well. It's possible, as I say, to do this MPI stuff on the containers, to do this more complicated running of networked applications on the containers. And we've got more detail on that on the Absena website and on the ARCHER2 website. You know, if you want to build a container like that, then you have to do a little bit of setup inside there, particularly with Singularity mpitch directory environment variables. So I've not shown you one of these before, but this is the sort of file which defines its container before you build it, and that will configure that kind of thing. The only challenge of it, so the Singularity and containers in general are a nice way of running sort of complicated or hard to install applications on a system like ARCHER2, and that's great, particularly if you have a pre-existing container. You can just pull it down and use it, with the caveat that we need to make sure we run it efficiently, but apart from that it should be fine. If you decide you want to build your own new container and you've not done containers before, you don't have an existing one, the only challenge with this is that to build a container, particularly to build a Singularity container, you actually need a system where you have root permissions, where you're a super user to be able to build it. And now, of course, you don't get access to be a super user on ARCHER2. So you can't build brand new containers on ARCHER2 as a user. You'd have to build them on your local system somewhere, a system where you do have permissions to do it, and then install that on the system. The other way we can do it is use a Docker container on ARCHER2 to build your Singularity container. So there is a Docker Singularity container on ARCHER2. It gets a bit complicated here, where we can run that build process through that as well, and that's also possible to try to do here, and we've got more details on doing that on the ARCHER2 website. So there's lots of software already available on ARCHER2. We have a range of compilers. It's pretty straightforward to bring a lot of applications and port them onto a system, but there are scenarios where we'll be missing libraries you need, or we'll be missing dependencies for your applications. In those situations, you can try and install those. You can talk to us and see if it's something that we can install centrally, or you can go down the container route, which is often quite heavily used in data science in other scenarios anyway. So we can bring on standard Docker containers and just run them on ARCHER2, with the caveat that I've mentioned all the way through, that we just need to make sure that we're doing these things efficiently. So if you bring in a container in which has MPI inside it, we probably want to make sure we're using the compatible MPI with ARCHER2, so we're getting the best network performance there. The good news is, of course, that Python and R are relatively straightforward. The there's optimized versions of Python and R already available. All we need to do is make sure we install our stuff on the home file, on the work file system, sorry, the work file system, not the home file system, and make sure that we are configuring that in such a way that we can pick it up inside our jobs when we run them. And as before, making sure we use the system efficiently is important. So placement and binding, as we've already seen, using the optimized math compilers, making sure we use up-to-date compilers and optimized compile options are always important, particularly if you're going to run jobs that are going to use large amounts of computational resources. If we can make them 10, 15, 20% faster by switching to a new compiler or by making sure the placement is exactly optimal, then that's a worthwhile thing to do. Any questions? Now, I'm sure you're sick of my voice by now. So what we can do now is go on to an exercise, the next exercise. Let's have a look. So you can keep going on exercise 1 if you've not already finished it. That's perfectly fine. There's a second exercise. Let me just share the screen here, where we can do similar things that we did with exercise 1, but instead of looking at memory bandwidth and looking at process placement, we can look at the file system performance you can get and the different file performance you can get with striping or not striping. This is using a parallel IO benchmark, but you can have a quick look at that. Now, if you don't think the file system performance is going to be an issue for you, if you already got a handle on what your file system stuff is, you don't need to have a look at this exercise. But it won't take you long. There's not a huge amount to do in it, but it just gives you a feel for the sort of bandwidth and performance you can get from the file system, and then what the striping, how you can do the striping and how that works. And then if you go into practical 3, there's something there to play around with installing your own Python software. And this can help because we're going to use some of this stuff later in the Python lectures and Python examples. And you can try starting running your own Python jobs there. Do the same for the R builds. And then you can have a look at playing with the container and see if you can do some of that kind of stuff with building your own containers and specifying and running those on ARCHER2, so you can have a look at that as well. And if of course you've got your own software you want to try out on ARCHER2, you can play around with installing that as well and ask us for any help. Any questions? If not, then we can do these 2 exercises until 1 o'clock, where we will break for lunch, and then we will come back at 2 o'clock to talk about parallel Python, or Python on ARCHER2 and parallel Python. And if you have any questions in the meantime, let me know.